Okay, this is chapter 5.6, inverse of a function. Essential question, how can you sketch the graph of the inverse of a function? What you will learn in this chapter is how to explore inverses of functions, find and verify inverses of nonlinear functions, and solve real-life problems using inverse functions. So here we go. Okay, so example 1 says, writing a formula for the input of a function. It says let f of x equal 2x plus 3. Solve y equals f of x for x. Okay, so what do they mean by that? Well, first thing you're going to do is rewrite the problem. So you write f of x equals 2x plus 3. Okay, just copy the original. Now it says solve y equals f of x for x. So the first thing I'm going to do is I'm going to change f of x to y and say that equals 2x plus 3. F of x just means what is y when x is some value. So that is f of x is equivalent to y, if you will. Okay, so now it says solve y equals f of x for x. In other words, get x by itself. So in order to do that, I'm going to subtract 3 from both sides. And that's going to give me y minus 3 equals 2x. Divide by 2, divide by 2. So then I get x equals, I'll just flip it over here, symmetry, y minus 3 over 2. So x equals y minus 3 over 2. Now it says find the input when the output is -7. So your output is y, and they want to know what the input was when y was -7. So you put -7 in for y. Okay, -7 minus 3 over 2. So then x is going to equal -10 over 2. And that simplifies to -5. Okay, so the input is -5 when the output was -7. Okay, so that's the example. Pretty simple. Let me recap. Rewrite the function. Substitute y in for f of x. Solve for x. And then plug in the output, which is y, to find what the input would have been. So now you should be able to do problem numbers 5 and 6 in the exercises. Okay, example 2. The book shows 2 methods, method 1 and method 2. I prefer method 2, so I'm only going to do method 2 in this video. So what that means is the first thing I always do is rewrite the problem. F of x equals 3x minus 1. Step 2, replace f of x with y. Step 3, put x over on the other side where y is, and put y over where x was. Okay, so you switch x and y. That's all I did there. The 3 stayed where it was, the -1 stayed where it was, x and y just traded places. Now I'm going to solve for y by adding 1 to both sides, and I get x plus 1 equals 3y. Now to get rid of that 3, I divide by 3, and I get y equals x plus 1 divided by 3. So this is the inverse function of this. Okay, so this can be rewritten as y equals, think of that 3 under the x and under the 1. So that'd be the same as 1/3 x plus 1/3. So if you look at it like this, it doesn't look like it's a linear equation, but if you rewrite it like this, then you see that the slope is 1/3 and the y-intercept is 1/3. So I'm going to graph this for you. So first of all, f of x equals 3x minus 1. So I'm going to go into Desmos. And I'm going to put f of x equals 3x minus 1. So that it was the original function. Then we came up with its inverse, which was g of x, and that equaled 3. It was x plus 1 divided by, let me see if I did that right. Where's my mouse? Okay. Let me see if I hit divide in here. Yeah, I didn't think so. Okay, so I need to put parentheses around this. So let me delete that. So it's going to be x plus 1 divided by 3. Okay, so that is the function that we got when we switched x and y and found the inverse. Now notice what's going to happen here. Y equals x. Okay, so the original function is this red one. The inverse is the blue. They're mirror images of the line y equals x. So they intersect at 1, 1. But if I come out here to 2, the point on the graph is 2, 1. Now, if I go diagonally or perpendicular to my line of reflection and go to the other side the same distance, that is the point 1, 2. So you have 1, 2 and 2, 1. So the x and the y replace each other, or they switch. Okay, and that's what an inverse function is. It's a function reflected across y equals x, and its reflection is the inverse. Okay, so that's what we're doing here. We're finding functions that reflect across y equals x, which is kind of neat. So after doing example 2, you should be able to do numbers 13 and 14. Okay, example 3 says finding the inverse of a quadratic function. Find the inverse of f of x equals x squared. So I'm going to rewrite the problem. F of x equals x squared. It says x has to be greater than or equal to 0. Then graph the function and its inverse. And I'm going to explain that in a minute. So the first thing you always do is change f of x to y equals x squared. Switch the x and the y. So now it's going to be x equals y squared. And then to finish this, I need to take the square root of each side. So I'm going to take the square root of x equals the square root of y squared. So this, and the square root of x, that's going to be plus or minus the square root of x equals y. Okay, so now I have y equals the square root of x, y equals negative the square root of x. And it says to find the inverse of x squared when x is positive. I'm only going to do positive numbers because negative numbers would be imaginary in the inverse. So I can't do those. So I'm going to graph x squared. So I'm going to go to Desmos. It says to graph the functions when you're done. So f of x equals x squared. I want to only do positives. Okay, so it's going to be, I think it's bracket, I can't remember. X greater than 0. Okay, so there it is, greater than or equal to 0. So I'm only going to do when x is positive. So that's only half of the parabola, because the inverse was g of x, if you will, equals the square root of x. So I'm not going to do the negative of the square root of x, because then what would happen is, I'll do it right now just to show you. Let's call it h of x. Okay, so remember there's what's called a vertical line test. So if I write x equals 4, I have x equals 4 and y equals 2 and negative 2. You cannot map an x value, a domain, onto 2 different y's, or it fails the vertical line test and it is not a function. So since this would not be a function, we do not want to graph this side. And that's why we didn't graph the negative side of the parabola, because that's what would have gotten flipped over. Okay, hopefully that makes sense to you. All right, so now I want to graph y equals x, and I want to get rid of that. So there you can see again the red function, the original x squared, reflected across y equals x is this other blue. Okay, so there they are graphed. So everything is going to reflect across y equals x if you do the inverse correctly. That's a way of checking. Okay, so now that I've done this example, you should be able to do problem numbers 23 and 24 in the problem set. Okay, you can use the graph of a function f to determine whether the inverse of f is a function by applying the horizontal line test. So I just mentioned that. So core concept here is horizontal line test. The inverse of a function f is also a function if and only if no horizontal line intersects the graph of f more than once. So the inverse is a function on this function because you draw a horizontal line anywhere on this function and it will never cross more than once. But the parabola obviously is not, like I explained in the last problem. So horizontal line test on the original function would be the vertical line test on the inverse. So if it fails horizontally, when you do this reflection, that horizontal line would become a vertical line. Okay, so that is a quick way to determine if the inverse is a function. All righty. Okay, example 4 is finding the inverse of a cubic function. Consider the function f of x equals 2x cubed plus 1. Determine whether the inverse of f is a function, then find the inverse. So I'm just going to graph this in Desmos. Okay, so let me clear this last problem. And what was the problem we were doing? 2x cubed plus 1. So f of x equals 2x cubed plus 1. We'll shift it up. So as you can see, if I draw a horizontal line right now, anywhere on this graph is only going to hit at one location. So this is the horizontal line test passes, so the inverse will be a function. Okay, so now we're going to find that. So it says determine whether the inverse of f is a function, then find the inverse. So I graphed it. It will be a function. So here we go. First step, write the original equation. F of x equals 2x to the third plus 1. Step 2, do you remember? Replace f of x with y, and that's going to equal 2. I'm going to make x red as well, cubed plus 1. So the only thing that changed here was f of x became y. Now we're going to switch x and y. So now x is going to go over here, and y is going to go here. Okay, really simple doing this. Inverse functions are really easy. It's a pattern. You just repeat the process, all the steps. Okay, so now we're going to solve for y by subtracting 1. And I get x minus 1 equals 2y cubed. Divide by 2, divide by 2, and I get x minus 1 over 2 equals y cubed. So now I'm going to take the cubed root of both sides, and that is going to give me y equals the cubed root of x minus 1 divided by 2. Okay, so that is the inverse of the original function. And now I'm going to graph that and show you that it does definitely cross or reflect across y equals x. So I want the cubed root of x minus 1 over 2. I'm going to call that g of x. Okay. And the way I have to do this is using the fraction, the rational exponent. So this would be the same as x minus 1 over 2 to the power of 1 over 3. Okay, and that's how I put it in my calculator. So x minus 1 divided by 2 to the 1/3. X minus 1 divided by 2. And then I want to put parentheses around that as well. because it's all to the 1/3. Okay, so there it is. And now if I graph y equals x, you can now clearly see that the red function reflected across the green line to the blue function, and the original function is a function and its inverse is also a function. Okay, so there you go. After doing this example, you should be able to do, oh, I think there's another example before I go on. Okay, so let's look at the next example. Okay, so next one, example 5, finding the inverse of radical functions. Consider the function f of x equals 2 times the square root of x minus 3. So the first thing you always do is rewrite the problem. Step 2, replace f of x with y. Okay, so I changed the colors of the variables because that's my reminder that they need to now switch locations. So now x goes where y is and y goes where x was. And now we're going to solve for y. To get rid of that 2 first, we're going to get x divided by 2 equals, the 2's cancel, equals the square root of y minus 3. To get rid of a square root, we square. To get rid of a square root, we square both sides. So this is going to give us x squared over 2 squared equals y minus 3. Be careful with that. Make sure you put parentheses around that and distribute your square. And then finally add 3 to both sides. This will give me x squared over 4 plus 3 equals y. So it said determine whether the inverse of f is a function, then find the inverse. Well, I found the inverse first. I didn't determine it yet. And so I'm going to graph 2 times the square root of x minus 3. So if I go to here and clear these, delete, and say f of x equals 2 times the square root of x minus 3. Okay, here is the graph. Okay, so because the range of f is positive, greater than or equal to 0, the domain of the inverse must be restricted to x is greater than or equal to 0. So the inverse of f is going to be a function where x is positive. So we have to restrict the domain, okay, or the range. We have to restrict the range. So since this is a function, because we can't put negative numbers in, then its inverse g of x will also be a function. Okay, and let me go back. What did I get? I got x squared divided by 4 plus 3, or 1/4 x squared plus 3. Okay, so this is going to equal 1 divided by 4 x squared plus 3. Okay, so notice the parabola is being shown here. I want to restrict that to x greater than or equal to 0. Okay, and then if I graph x or y equals x, then you see these two functions get reflected across y equals x. Okay, this is always your check to see if you did the inverse correctly. If your second function does not reflect across y equals x, you did something wrong. Okay, so there's the last problem. And so after doing examples 4 and 5, you should be able to do problem numbers 35, 36, and 38 in your problem set. Okay, so now we're going to learn how to check to see if two functions are in fact inverses of each other. So let f and g be inverse functions. So if f of a equals b, then g of B has to equal A. So in general, this is called the composition of functions. F of g of x equals x, and g of f of x equals x. Now, this might be a little confusing at first, but I'll try to explain it the best I can. All we're doing is plugging one function in to the other. So if I want to find f of g of x, what does that mean? Well, g of x means what is y when x is something in g, and then you find that numeric value and you put it into f. So that's what we're going to do here. We're going to actually put a function into the other function. So what that means is I have this function right here, 3x minus 1. And I'm going to take this whole function of g and substitute it in for x. So the 3 is going to be there. And I'll put a parentheses here. And instead of writing x, I'm going to write g of x. Well, what is g of x? It's x plus. Actually, let me show that first, what this actually means. F of g of x would be 3 times g of x minus 1. So all I'm doing is putting g of x where x is. Okay, hopefully that makes sense to you? And then we're going to replace g of x with what it's equal to. So g of x is x plus 1 divided by 3. So I'm going to put that in place. And minus 1. Okay? So the 3 and the 3 will cancel. And then when I simplify that, I get x plus 1. And then this minus 1 out here. And 1 minus 1 is 0. So I get x plus 0, or simply x. And so if f of g of x equals x, and then you do the opposite, g of f of x, and that also equals x, then you have confirmed that they are inverse functions. So now I'm going to do g of f of x, and that's going to equal. So now I'm doing g of x. So instead of putting x here, I'm going to put f of x where the x was, plus 1 divided by 3. So g of f of x is, now I'm going to substitute in f of x. Well, what is f of x? It's 3x minus 1. I'll put that in parentheses so we can remember where it came from. So 3x minus 1 plus 1 over 3. Okay, so just ignoring those parentheses now, it's 3x minus 1 plus 1. Minus 1 plus 1 is 0. That leads to 3x. Hey, stop. That leads to 3x. 3x divided by 3. Well, the 3's cancel, and I get x. So f of g of x equaled x. G of f of x equaled x. So that proves these two functions are inverse functions. And I'll show you in a graph. So f of x is 3x minus 1. Okay. So f of x, equals 3x minus 1. And of course, I'm going to graph the y equals x line. So then the inverse was g of x equals, and where was that? It's x plus 1 divided by 3. So x plus 1 divided by 3. Okay, so as you can see, they do reflect across this blue line, y equals x. Okay, so that's what they look like graphed. So without graphing, this is how you check to see if two functions are inverses of each other. So now you should be able to do problem numbers 49 and 50 in the problem set. Okay, now we're going to solve a real-life problem. In many real-life problems, formulas contain meaningful variables, such as the radius r in the formula for the surface area S of a sphere. S equals 4 pi r squared. Do you remember that from geometry? Okay, so anyway, in this situation, switching the variables to find the inverse would create confusion by switching the meanings of S and R. So when finding the inverse, solve for R without switching the variables. What? Okay, so let's take a look. It says, find the inverse of the function that represents surface area of a sphere. S equals 4 pi r squared. Then find the radius of a sphere that has a surface area of 100 pi square feet. Okay, so first thing we're going to do is solve for r. Okay, remember it says without switching. So I'm going to get r by itself. So in order to get r by itself, I want to divide both sides by 4 pi. Okay, if I divide by 4 pi here and divide by 4 pi here, I get s divided by 4 pi. Why am I writing a 5? Because it rhymes? No, it doesn't. 4 pi equals 4 pi divided by 4 pi is 1 r squared. Now I need to take the square root of both sides, like so, and I'm going to get plus or minus the square root of s divided by 4 pi equals r. Okay. Now, radius can't be negative, so always think about what types of problems you're doing. A radius cannot be negative because a radius is a distance between the center of the circle and its edge, and obviously distance can't be negative, so we're only taking the positive side, so I don't even have to write the plus minus. So r equals s over 4 pi. Okay, so now it says find the radius of the sphere that has a surface area of 100 pi. Okay, remember S is surface area. Surface area is right here. So now I'm going to write R equals the square root of, and now I'm going to substitute S in for 100 pi. Okay, 100 pi divided by 4 pi equals R. Well, the pi divided by pi cancels, and 100 divided by 4 is 25. And the square root of 25 is 5. So the radius is 5 if the surface area of the sphere is 100 pi. Okay, and so that's how you do that problem. So now you should be able to do problem number 53 in your exercises. Okay, that brings us to the end of chapter 5.6. These are the problems I assigned. Hopefully you're doing them as you went. Thanks for watching and have a great day.